Thanks for joining the presentation. Today I'm going to present our work, Geometry-Driven Progressive Warping for One-Shot Face Animation. This is a joint work with Fayez Amjadi and Ilya Zakov. So what's the task? With many focus on face reenactment, if you look at the figure on the left, we have two images as input, one as the source image and the other as the driving image. The driving image can be same identity as the source, but can also potentially be a different identity from the source. Given an input, the model generates an output image that mimics the motion of the driving subject, but preserves the identity and appearance of the source subject. Here are two examples on the right. There are basically two classes of methods for this task. One is warping-based and the other is mapping-based. The central idea of the warping-based model is the estimation of a displacement field between the source image and the driving image, and then warp the source pixels or features to the driving image space. Mapping-based models generally perform a mapping from X to an output image conditioned on the identity and appearance of the source image. This X can be any motion descriptors, facial key points and landmarks, and their variants are often used in the literature. In this work, we will be focused on warping-based model, and we will try to improve the quality of displacement estimation for this type of method. So how do we improve the quality of displacement estimation? We propose two ideas. One is the geometric guidance, which acts as a strong guiding signal for the model to predict accurate displacement field. We designed two geometric patterns for this. One is geometric displacements, and the other is post-neural codes. The other contribution is a novel progressive warping module, which helps generate displacements that are more spatially aligned with the driving image space. Let's start with the first pattern we use for geometric guidance, the geometric displacements. As a first step, we feed a 3D or 3D morphable face model to the source and driving images to obtain their meshes. Specifically, we use Flame as the underlying 3D and Deca as the feeding algorithm. Next, we compute 2D displacement vectors V using the meshes by projecting them to the image space and compute their offsets, as you can see in this formula. And then we render a two-channel image by using the topology of the driving mesh and the V as the vertex color. This two-channel image is the geometric displacement. The geometric displacements are high quality and can transform a point from source image space to the driving image space very accurately, but up to some fitting error that could happen in a 3D fitting stage. The other geometric guidance we use is the post-neural codes. Similar to geometric displacements, we need to obtain the source and driving meshes from 3D fitting in the beginning. Next, we attach a d-dimensional embedding vector to each vertex of the template mesh. If we have n vertices, we end up with an embedding matrix E, whose shape is n by d. Finally, we take the embedding vector of each vertex as its color and render the d-dimensional image, and this d-dimensional image is the post-neural codes. The whole process is differentiable, so all this set of embeddings are learnable at training time. So far so good. Actually, we have a problem. No matter geometric displacements or neural postcodes, both rely on the 3D face mesh. For regions not modeled by the 3D face mesh, there's no way we can achieve motion transfer. For example, hair, glasses, hats, and other accessories. Therefore, we need another module to predict the full displacements that can cover the whole head region and its surroundings. To that end, We propose the Progressive Warping Module, or PWM, to estimate the full displacement field. The PWM is a plug-in module in a decoder. It works by using the rendered geometric displacement image or post-neurocode image as guidance, and it alternates between feature realignment and displacement estimation. Let's take a closer look at how PWM works with this diagram. At each pyramid level, PWM takes the realigned feature from the previous level as input, which goes through a spade layer with the geometry guidance as modulation. Then it goes to another conv layer to get the estimated full displacement field. We use this estimated full displacement to warp the encoder feature to obtain the realigned feature at current pyramid level. As shown in the dashed line, the realigned feature will also be used in the next pyramid level. And by doing this iteratively, the PWM alternates between feature realignment and displacement estimation, so we can get very high quality displacement. Here's an overview of the model architecture. The model has a couple of conv layers as encoder and a couple of PWM modules as decoder. Within each PWM module, we predict the full displacement field and use that to warp the encoder feature, so we can get the spatially aligned feature for the next PWM to use for more accurate displacement estimation. Here are the experiment results. We evaluate our method and other baselines on the Voxelab 1 and Voxelab 2 datasets. On each of the datasets, we compute a set of metrics for same-identity and cross-identity phase reenactment, respectively. Results are presented in this table. As can be seen, there are 3 model variants for our method, depending on which geometry guidance we use. For example, we have PWM with geometric displacements, PWM with post-neurocodes, and PWM with both types of guidance. Each model variant may achieve slightly different performance on the metrics, but our method always outperforms other baselines regardless of the geometry guidance in use. One interesting thing we found is that geometric displacements tend to achieve better image realism, while post-neurocodes tend to achieve better motion accuracy. For example, PWM plus geometric displacements in the table generally has better numbers for FID and CSIM, while PWM plus neurocodes has better numbers for AKD, AED, and APD, which are the metrics for key point, expression, and pose accuracy. We believe this is because geometric displacements have less spatial alignment constraint in a driving image space. There are a couple of reasons for this. First, it only encodes relative motion. Second, it's less constrained on the facial geometry and semantics. Third, by trading off motion accuracy for image realism, it can do less aggressive motion change and less pixel synthesis, therefore easier to achieve better image realism. To validate our conjecture, we add 3 additional metrics, L1, SSIM, and LPIPS. These metrics are computed pixel-wise and averaged over spatial dimensions, so they can reflect how synthesized images are spatially aligned with the ground truth. We can see the geometric displacements actually have worse numbers for those metrics, which is another evidence for the spatial alignment issue. So far, we have been using the flame as the underlying 3D-MM. To justify the effectiveness of our method, we also train another model with the BFM as the underlying 3D face model. As shown in this table, BFM is slightly worse than flame, but still outperforms other baselines by a large margin. Here are the qualitative results. Our method generally generates images with better realism and sharpness compared to other baselines. For more videos, please refer to our supplementary materials. In addition to face reenactment and motion transfer, we can also do face editing by changing the shape, expression, and pose parameters of the underlying 3D face model. Here are some examples. In summary, we designed a model driven by 3D face geometry and proposed two types of geometric guidance, including geometric displacements and posed neural codes. And we also propose a novel progressive warping module for displacement estimation. We conduct extensive experiments to demonstrate the effectiveness of our method. That's it, and thank you for your attention.